Now, students, as we have completed atom molecules and chemical reaction, now I am going to start is matter pure. So for that, we are going to give you the digital content for the first 2 3 days, then followed by the explanation part of the chapter, each part wise. Okay, students. So watch these videos, make sure that whenever you watch them, keep a pencil with you, or like place a textbook in front of you, so that you'll get the clarity of the concepts which are there in the explanation part and which are there in the textbook part. Okay.
Hello friends, this video on Is Matter Around Us Pure part 12 is brought to you by examfear.com. No more fear from exam. Let's see how can we obtain gas from the air. Air we know has oxygen, has nitrogen, has argon, has other gas also. So we talk about the composition. Oxygen is almost 21.9% by volume. Nitrogen is almost 78.1% by volume. Argon is 0.9% by volume, and another is only 0.1%. These are by volume. And we have to separate them. To separate this, we know that we need some physical property. So let's see the boiling point. Nitrogen, the boiling point is 77 Kelvin. Argon is 87 Kelvin, almost. Oxygen is almost 90 Kelvin. And carbon dioxide, other will ignore. Let's try to focus on oxygen and nitrogen itself. So if you see, there is a difference in the point of almost 13 Kelvin. And the 13 Kelvin is actually less than 25 Kelvin. So we have to use some fractional distillation here, right? So, but we know that at least there is a difference in the boiling point. And we know that air is nothing but homogeneous mixture. Okay. Homogeneous mixture. It's a colloidal actually of oxygen, nitrogen, argon and other gas. And these have different boiling point. So we can actually, and the difference in the boiling point is less than 13 degrees Celsius in this case. So we can actually separate them by fractional distillation. Okay. So what we can do here is, we can actually take air, will compress it by applying pressure. It also cool down. When you cool it and when you compress it, you get liquid air. Correct? To liquefy something, either you increase the pressure or decrease temperature. Here we are doing both. Once we get this, what we do is we warm slowly in the fractional distillation. And with this, when you warm slowly, the gas separates out at different height because they have different boiling point. So if you see, nitrogen has the minimum boiling point 77 Kelvin. It will evaporate first, okay, and it will become, for example, if you see here, this is air under high pressure and cool temperature. What we are doing is we are getting a liquid air, right? This is the normal air. We are putting, it is the normal air. We are putting the filter also to make sure that all the particles are, suspended particles are gone. And then under high pressure and under cold condition, we are making it almost liquid. Okay. Now once we have the liquid here, now we have liquid here. Now we slowly start warming here. So if you see here, this side is more hot, this side is cold. This area is 77 Kelvin temperature, this is 90 Kelvin temperature. Don't increase temperature very high, but this is this range. So the moment here the liquid air comes out, right, through an expansion jet, because it's all liquid here. Till this part we have all liquid. Now the liquid air comes out and we reach this temperature of 77 K. What will happen? The moment you have 77 K, the gas will come out. And which gas will come out? Nitrogen gas will come out. And the gas you will fit from some pipe here and you will collect nitrogen gas. Okay. Okay. When argon also has a low temperature, we will get some argon also. Now the remaining gas will come here. The liquid, it is still in liquid form. The gas we have collected as nitrogen. The remaining liquid will come here, and that will be the liquid oxygen, because oxygen is again almost 90 Kelvin temperature. So we'll collect most of the nitrogen, almost 78% nitrogen will be collected here, and remaining will come here, and that will be liquid oxygen. So if you see here, this is the main point, and please note the temperature is differentiated. Here we maintain the temperature of 77 K. If you maintain the temperature of 77 K, not more than that, because if we make it 90 K here, oxygen will also evaporate and will be collected in this tank. So, but this is actually fed to a tank, and in this tank we want to collect only oxygen. Right, so what we do is we make sure the temperature is 77 K here. So with that only oxygen gets evaporated here, because oxygen has the boiling point of 77, and we collect the oxygen. The remaining liquid air is passed on here, and the remaining liquid air typically has more oxygen. So only the nitrogen is collected here. Hope you understood the flow. So let me explain this once again. So here we have liquid air, and this part which you see actually is connected to a tank, and this is nitrogen. This is a liquid air. This is a liquid. Now when you maintain the temperature of 79 K here by applying some heat, maintain this temperature. The moment liquid air is heated to 77 Kelvin, in liquid air nitrogen has the boiling point of 77 K. Oxygen has 90 K. So nitrogen will convert into gas, and this nitrogen will be converted into gas, cooled down and collected here. The remaining liquid air will go here because of the flow, because there is a flow, it will be collected here as liquid oxygen. Okay. The next is we'll try to purify copper sulfate sample. Okay. So in this case there is a copper sulfate sample. This is a copper sulfate sample, and this is impure. We have to purify it. How can we do this? It has some impurities. We don't know the quality of impurities. So what we can do is we can actually dissolve this copper sulfate solution into water. Okay, some minimum amount of water that is required, and we can actually filter out some impurities. The big stone particles actually can filter out. Once that is done, let it dissolve. Actually dissolve the whole copper sulfate solution, and then you filter out. You get this solution, and then you can filter this out with this filter paper, so that if there is some small or big stones particle here, that you can actually filter out. Okay, and then once that is done, and then you again keep in this kind of jar, and then you allow it to cool down. If you allow it to cool down, you filter out. Once you filter out, right, so if you see now, if you filter out, and then you actually allow it to cool down. If you let it cool down, there is no heat here. If you cool down, let it cool down, then you will see that it will become, water will still be here, but this will become transparent water, and the copper sulfate crystals will get deposited here, and this process is called crystallization. Okay, so what we have done is, so we have taken some copper sulfate and we have dissolved this in water solution, and then we have filtered out some impurities, the big impurities. All these big impurities you see are filtered out here. Whatever we got here, solution, then we cooled it down. Actually not heat, we will cool it down. We'll cool it down, and then we'll see that after some time the crystals of copper sulfate will come out. Okay, same process actually, whatever NaCl, the common salt we eat, that is also purified into seawater. Seawater has a lot of salt, and the same process is used to extract salt from the seawater. Let's see how we get the drinking water purified. Whatever water we get in the city actually is purified by the government, and there's a whole big process for that. So this is the impure water which we get from reservoir. I'll say this is the impure water. The first thing is done is this water is put into a sedimentation tank. Here water is allowed to settle down for some time, maybe 2-3 hours. So here what happens is solid particles, they get settled down, right? The solid particles get settled down here. So we'll see here the solid particles get settled down here, and that's why it's called sedimentation tank, because sedimentation process is taking place here. Now this is relatively pure water. It goes from this tank to a tank called loading tank, right? So here we don't have sedimented impurities. Here we have water without sedimented impurities. So I have relatively pure water, but it will still have impurities in it, which are fine impurities. Now this sedimentation, this water is now again allowed to pass through a filtration tank. So in this filtration tank, we have sand, we have gravel, we have coarse stones. So this sand is on the top layer, then we have gravel, and then we have coarse stones. So what these does is, these are charged sand, okay? So when water flows through it, these particles which are impurities, they get attracted towards this sand particles. These impurities gets attracted towards the sand particles, and thus we get more pure water. So we see it has little impure water, it has more pure water by the time it flows through the filtration tank, because the impurities get attracted by this charged sand particles. So here we get little pure water. So once I get pure water, we actually do chlorination. So chlorination kills the bacteria. So we add some chlorine. So with that you kill all the bacteria, and then you get water. And this is the pure water for drinking. Okay, please note here, this sand filters, they have charged particles. These charged particles attract the impurities from the water. This is the typical process by which the impure water, typically from the lake or from any water body, a river, is purified, and you get that purified water in the home. Let's take some numerical now. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again. Hello friends, this video on Is Matter Around Us Pure part 14 is brought to you by examfear.com. No more fear from exam. Understand the physical and chemical chain. Let's see the classification of the pure substance now. So this part we have seen, the matter is classified as mixture and pure substance. The mixture is further classified as heterogeneous and homogeneous. Heterogeneous was suspension, homogeneous was colloidal and suspension. This is part we have seen. Let's see the pure substance. The pure substance is further classified into elements and compounds. And elements are further classified into metals, non-metals, metalloids, and compounds can be organic, inorganic, covalent, ionic. So let's first study elements and compound. Let's first study the elements. See, all this chemistry has progressed mostly in the last 500 years. Prior to that, the chemistry was not popular. It was not very famous. In fact, in 1661, this guy Boyle, Robert Boyle, he was the first to introduce this term element. Prior to 1661, this term element was not there. He coined this term element, but he could not give a correct definition of element. He was doing experiments and he thought this is the pure form of substance, but he could not give actually a very pure good definition of element. He coined this term element because a lot of elements were getting discovered, new things were getting discovered, and he gave this term element. In fact, in 1760s type, this guy Lavoisier, I don't remember the exact time, 1760s, that time this guy Lavoisier, he defined the element, and he defined the element as basic form of matter. So as per his definition, element is the basic form of matter that cannot be broken down. That cannot be broken down into simpler substance, by chemical reaction. So for example, if you take gold, if you take hydrogen, if you take carbon, if you take nitrogen, these things you actually can't break further. See, common salt has NaCl, you can break into sodium and chlorine, but once you get sodium, can you break it further? You can't break. So the definition is, it is a basic form of matter that cannot be broken down into simpler substance, right? That is element. If you see, all these elements are listed in the periodic table, and out of these, some 92, I think, yeah, till here, run to 92. These are natural, and post 92 they are called transuranium or transuranious. I don't remember the term exactly. These are all man-made. They are prepared in the lab by bombarding some particles with these, but they are all man-made. But 92 are naturally occurring, because once you increase the atomic number, the stability of this element decrease, and we will study about these in the higher classes, why we don't have more than 92 naturally occurring elements. Okay, so as per today, there are huge number of elements, and out of that 98, not huge, 100 plus, 108 something, 98 are natural and other are man-made. These elements, hydrogen, helium, lithium, typically whatever you see in periodic table is element. Let's understand. Periodic table lists down all the elements. The elements are nothing but the basic form of matter that cannot be broken further into simpler substance by any chemical reaction. Okay, and based on the property, metal can be further classified. I mean, element can be further classified as metals, non-metals, and metalloid. So we'll see typically this side we have metals. We'll see further this side we have non-metals, and somewhere here we have metalloids. I just drew a rough figure, but actually this is the trend. These are metals on the left hand side, right side we have non-metals, and somewhere in the middle we have some metalloids. Okay, silicon, boron, those are examples of metalloids. Now we'll discuss what are these metals, non-metals, and metalloids. But to understand this, elements are the basic form of matter that cannot be broken further into simpler substance by any chemical reaction. This definition came in 1700s. That means all these advancement in chemistry happened in the last few years only. Okay, so let's understand what is metal. See, metal typically have shine. So if you see metal, you think of metal, think of gold. Gold has shine, right? And or think of silver as well. In fact, 90% of the metal are silvery color. Only few of them are golden color. Copper and gold. These two are golden. Most of the metal, if you see, are silver. If you take aluminium, if you take zinc, if you take silver, if you take sodium, if you take mercury, you take most of the uranium, most of the metals, actually, let's take these metals. Most of the metals are silver in color. Potassium, most of them are silver in color, 90%. Talk about silver, you see, they conduct electricity, right? So first things, they have shine that we have seen. That's why they are used for making jewelry. Okay, they are mostly silvery gray or golden color. They conduct heat and electricity, and that's why they are used in wires. They are ductile. They are ductile, that's why you can draw into wire. So they are ductile. So we can draw into wire by hammering or something. They are malleable, and thus you can make thin sheets. Right? They are malleable, this is for ductile. Thin sheets. This is, they are good conductor of heat, I told. Good conductor of heat. And that's why, if you see, they are used in pans, frying pans. They are good conductor of electricity. That's why they are used in wires and electrical equipments. So let me write here as well. Good conductor of electricity as well. They are sonorous. When you hit it with some other metal, it on sound. And that's why they are used for bells. So that property is called sonorous. They have different sound. Some people actually by the sound can make out which metal it is. Okay, sound when it hit. And mercury is the only metal that is liquid. Mercury, this is, if you think of mercury, think of thermometer. In thermometer you have mercury here, this mercury. So mercury, since it is the only metal, it is an exception. Mercury is only liquid metal. At ST. All other metals are solid. Okay, please note, mercury is the only liquid metal. So this is all about metal. They have shine, they are ductile, they are malleable, they are sonorous, they conduct heat and electricity, and mostly they are solid. Talk about the non-metal. They have variety of colors. If you see, these are for phosphorus, 3 different colors for phosphorus. Okay, this is sulfur, yellow color. This again, if you see carbon is black color. This iodine is all the more dark color. And if you see, this is bromine, red color. Right? This is chlorine. So they have different colors. This is fluorine, I think. So they have different colors. You see, it start from yellow, red, black, again dark yellow. There's so many colors. There's so variety of colors. Variety of colors. And they are poor conductor of heat and electricity. They are not good conductor. They are poor conductor. Okay, they don't have shine. No shine. They don't have shine. They are dull actually. They don't have. They don't create sound also. So no sonority. If you want to imagine, can you imagine hitting two coal pieces and you feel that metallic sound? No, it doesn't give that kind of sound, right? So it is not malleable. You can't think of non-metal. Think of coal. Can you create a thin sheet out of coal? No. So it is non-malleable. Can you create thin wire off of coal? No. So it is non-ductile also. And they are typically soft. Coal is typically soft. They are not hard like metal. So the property is totally different. Metal is hard. This is soft. Metal is ductile. It is non-ductile. Metal is malleable. It is non-malleable. Metal is sonorous. It is non-sonorous. Metal has sign. It has no sign. Metal is good conductor of heat and electricity. It is not good conductor of heat and electricity. Metal is generally 90% silver and very few golden. But here they have a variety of colors. So in all the properties, metal and non-metal are totally different. They are totally anti. Let's see a third type of metal, metalloids. They are somewhere between metal and non-metal. So this metal is on the left hand side, they have different property. Non-metal is on the right hand side, they have different property. Somewhere between them is we have metalloid. They have property which is almost some property of metal, some property of non-metal. We'll not discuss much about metalloids. Example I can give you: boron, silicon, germanium. These are typical example of metalloids. Silicon is used to make chips. Boron is used to make boron glasses for the lab. And germanium is also used mostly in that field, electronics field. All the computers have this silicon. Let's see some facts about these metals. The fact is, the number of metal known to us is more than 100. So 100 plus, 115 plus metals are known. Sorry, elements, 115 plus elements are known to us. Okay, out of that I told till 98 is natural. Atomic number 1 to 98 is natural. Other are all man-made in the labs. Hydrogen to uranium is called natural. Other are man-made. And most of these are solid. Most of these are solid. Only 11 elements are gas at STP and 2 is liquid at STP. 2 is liquid, 1 is mercury we have seen, and the other is bromine. Apart from that, most are, you can do your maths, mostly here 79. 79 is solid, and I'm talking about the natural one. Artificial one are again solid, and most of them they are produced in such a tiny form that their state cannot be determined. Let's talk about the natural one. Natural one, 79 is solid, 11 is gas, 2 is liquid. Okay, these are the key facts about the elements. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again. Hello friends, this video on is matter around us pure part 15 is brought to you by examfear.com. No more fear from exam. Let's talk about the compound now. Element we have seen, they are the one which we can break further. But compound are substance which composed of two or more elements, 2 plus elements combine to form compound. Right? And they combine chemically. For example, hydrogen and oxygen, there are 2 elements, they combine to form water. and they are combined chemically in fixed proportion. Right, 2 plus elements combined chemically in fixed proportion to form compound. For example, HCl, hydrochloric acid, has one molecule of hydrogen, one molecule of fluorine to form HCl. H2SO4, sulfuric acid, 2 molecules of hydrogen, 1 sulfur, 4 oxygen to form hydrochloric acid. Carbon dioxide, 2 molecules of oxygen, 1 molecule of carbon to get carbon dioxide. All these are examples of compound. The easiest example you can think of is water. Right? So compounds are 2 plus elements combined in a fixed proportion chemically to form compound. Compound actually you can further break into elements. Okay, there are tons of compounds, and we have further classified compounds into ionic compounds, covalent compounds, organic compounds based on different properties. So we'll study about these things in the later classes. As of now, you don't need to understand those concepts. Let's take a different mixture in compounds once again. Both look similar to it, right? In compound we have various elements combined in a fixed proportion. In mixture again we have various elements or compound we can mix. See, you can take elements, for example, you can take hydrogen, you can take oxygen, you can just mix them without any chemical reaction, then it will be a mixture. But if you have hydrogen and oxygen and you react at some temperature, it becomes water, this is a compound. Okay, you just mix some elements of compound, you get mixture, but elements, if they react, they form new compounds. In a kind of mixture, the composition is variable. You can have 5 moles of hydrogen, 8 moles of water. You can have any proportion, doesn't matter. But in this, you have to have fixed composition. For example, for water, you should have 2 hydrogen and 1 oxygen. The composition is fixed. Right? These mixtures have the properties of the constituent substance. For example, hydrogen and oxygen, if you mix, just mix, they don't react, then the final property will be similar to hydrogen and oxygen. When you talk about compound, the water will have totally different property as compared to hydrogen and oxygen. So the final output will have totally different property. In case of mixture, these particles actually here itself can be separated by some physical method. But once it has become compound, you need some chemical method to break this bonds. Correct? Because it's the chemical process actually, what I can say. And this is a physical process. So that is the whole reason why we explain so many physical and chemical change. This is a chemical change. So 2 elements, different 2 or plus more than 2 elements combine chemically to form compound. 2 or more than 2 elements or compound itself, they combine physically to form mixture. Since it is a physical change, you can actually separate them by physical method. Since it was a chemical change, to separate them you need chemical method only. Let's do a recap. A mixture contains more than one substance mixed in any proportion. Mixture can be separated into pure substance by some techniques, and we have seen so many techniques here. Evaporation, distillation, sublimation, chromatography, so many things we have seen. A solution is a homogeneous mixture. That is something we have seen, which has 2 or more than 2 substances. And the major component is called solvent and the minor is solute. This is typically not always true, but 99% cases this is true. In some cases this may not be true. Right? The one which dissolves, that is solvent, and the one that is dissolved, that is solute. That is a better definition. But for now you can assume this definition. The concentration of solution is the amount of solute present per unit volume at any given concentration. That is concentration. Right? It can vary. But when you talk about solubility, that is the maximum amount of solute a solution can hold at a given temperature and pressure. Materials that are insoluble is solvent and have particles that are visible to naked eyes. Okay, they form suspension, and suspension is a typical heterogeneous mixture. Right? Colloidals are also, there is doubt here. Some people say heterogeneous, some people say homogeneous. In fact, as per CBSE, it is heterogeneous, but I personally feel it is a heterogeneous mixture. Sorry, it is a homogeneous mixture. That's my assumption. But there is still a debatable topic on this. Here, the particle size is too small that they cannot be seen by naked eyes, but they are big enough to scatter light, and thus they show Tyndall effect. And they are very useful in industry. They have dispersed phase and dispersion medium, and we have seen so many examples of the colloidal solution. Milk is the one example. Pure substance can be elements or compound. Only two options we have for pure substance, or I can say pure substance can be classified as elements and compounds. Element is a form of matter that cannot be broken down by chemical reaction into simpler substance, a definition by Lavoisier. And the compound in substance is composed of two or more different type of elements that are chemically combined in a fixed proportion. So please note these two words: chemical elements chemically combined fixed proportion to form compound. And the properties of compounds are totally different from its constituent particles. But in case of mixture, the properties of the mixture is similar to the constituent particles. Okay. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again. Hello friends, this video on Is Matter Around Us Pure Part 16 is brought to you by examfear.com. No more fear from exam. Let's take some questions here. Which separation technique will you apply for the separation of the following particles? Sodium chloride and its solution in water. So I have here NaCl and water. Now we see that sodium chloride in water, NaCl is non-volatile, but water at 100 degrees Celsius is volatile at 100 degrees. So what we can do, we can just do evaporation here. So if we do evaporation at 100 degrees Celsius, water will convert into gas and the sodium particles NaCl will actually be here itself. It will be somewhere here. The next is ammonium chloride from the mixture containing sodium chloride and ammonium chloride. Sodium chloride is non-sublimate. Ammonium chloride is sublimate. Be something we know. Since one is sublimate, one is non-sublimate, what we can do is, this is the order of ammonium chloride and sodium chloride. Since one is sublimate, one is non-sublimate, we can use sublimation process here. So we can use sublimation process here. Small pieces of metal in the engine oil of the car. So if you see an engine oil of the car that is used, it will have small pieces of metals. For example, this is an engine oil and this is small piece of metal. Want to separate them. Since these small pieces are pretty big, you can actually use a filtration process. You can use some sieve or filter paper to actually filter out the small metal pieces. So you can say it's a filtration because these particles are big enough to be seen by naked eyes as well, and it will not pass through filter paper. So we can typically use filter paper to separate this particle. Different pigments from the extract of the flower petal. So we have seen these flower petals have different pigments, and to separate them we use chromatography, because all these pigment particles, for example, you have black color dye also, it will have red, blue, pink, yellow, all these colors, and these colors have same boiling point, melting point. So actually you can't separate by evaporation process and other process. So but they have different stickiness tendency to some solvent. So typically we use chromatography in this case. Butter from curd. We know that the butter is lighter than curd. So what we can do is, if you want to take out from this curd, if you want to take out the butter, so what you can do is you can actually use centrifugation. In centrifugation also, the lighter particle will come up and you will get butter from curd. Okay, that is one. The next is we have to find out more. Oil from water we have to separate. So there's oil and water, and these we see they don't mix, and oil is lighter. So if you keep this suspended for some time, what will happen is the oil will come up and the water will settle down because the water is heavier. So we can actually use a separating funnel here. So we have shown you this. You can watch some of the previous videos in the same chapter where we've explained this. The next is tea leaves from the tea. Let's suppose you're preparing tea. This is a tea and it will have some tea leaves when you prepare, and you have to separate. Now since tea leaves are big in size, you can actually use sieve, that is a filtration process, to separate tea leaves from the tea. The next is iron pins from the sand. Sand has some iron pins. So now if you see, what you can do is, one thing you can do is you can actually use the magnetic property. This iron is magnetic, right? It is attracted toward magnets. The sand is non-magnetic. So you can use that as well. Or if the iron particles are big in size and sand is small, you can use filtration also, if that is the case. But if the iron particles are very small, almost same size as sand particles, then you can't use that, right? Because in the filter, whatever filter you use, both sand and iron particles will pass through. So you have to use magnetic property, okay, magnetic separation. But if there's a difference in the size, you can actually use filtration. But here I'll go for magnetic property because that solves both the purpose. In all the scenarios, this will work. Wheat grain from the husk. This is husk. This is how it is cultivated. From this, you have to take out wheat grains. So what we do is we first hit it hard. You hit it hard, then both get separated. And this, the outer layer of the husk is light. It is very light. It's a very thin film. It's very light. But wheat is heavy. So what we can do is, since one is heavy, one is light, we can use winnowing. Winnowing is you keep this and try to put it down, and some wind blows, and with that wind, the light particles it flows in the air, and the heavier particles settle down. It's like this. You have this kind of structure, and you put a fan here. Let's suppose fan will blow air. So in this, you have mixture of the whole grain plus husk here. Now if it comes down, since there's a fan here and the wind blows, the husk will go here and the grain will settle down. So what will happen after this is all this grain will come settle down here, and the husk will flow, and all the husk will be collected somewhere here because of the fan or wind, heavy wind actually, because this is particle is lighter, husk is lighter, it will float in air, and the grain is heavier, it will not float in air, it will settle down. Okay, you can try this kind of experiment in home actually, where you take one light particle and heavy particle and you try to throw in front of a fan. You will see that the lighter particle will go and settle down somewhere far, but the heavier particle will fall down immediately. Okay, you can try with maybe a small piece of paper, and you can take some dal, heavy dal, or you can take wheat itself. You take some wheat and mix it with some small piece of paper if you don't get the husk, and then you have the mixture, and then take it in front of some fan and try to throw it or try to put it down, and then from the wind speed this paper particle will come and settle down or flow in the air, and the wheat will actually be collected here. Okay, fine mud particles suspended in this air. So fine mud particle which is suspended in this water, we can actually use sedimentation process. We can leave it for some time, all this will settle down, and whatever you have, you can use the filtration process also. If you want to really filter it out better, or you can use centrifugation for immediate sedimentation as well, or you can leave it for some time, it will come down. So many steps you can use actually. You can use sedimentation, you can use filtration, you can use centrifugation. You can use all three combined actually in this. Okay. How will you confirm that the colorless liquid given to you is pure liquid? For example, a stranger comes to you and he gives you a glass of liquid, and he asks you, tell me if it is water. See, a colorless liquid can be acetone, it can be alcohol, it can be anything, it need not be water. How will you confirm? See, what you can do is, for this, you can actually boil this. If you boil the colorless liquid, and if it is pure water, everything will start boiling at exactly at 100 degrees Celsius. So we know one property that pure water boiling point is 100 degrees Celsius. You keep a thermometer as well here, and you just boil it at the rate 100 degrees Celsius only. So if it boils at 100 degrees Celsius, there is a 90% chance it is water. To double check, what you can do is you can actually let the whole water boil. You can take a small sample of water and you can let the whole water boil. So if everything boils up, there is nothing left, there is no residue left, that means it was a pure water. If not, you will see some salt or something, some sugar, that means it was not a pure water, it had some impurities as well. So with that you can actually find. The first thing is knowing the fact that the boiling point of pure water is 100 degrees Celsius, you confirm it is water, and double check, you boil the whole sample of water and make sure nothing is left in the vessel. If nothing is left, that means it is a pure water. Which of the following materials fall in the category of pure substance? Is ice a pure substance? See, if it is made from pure water, yes, ice is pure substance. Is milk pure substance? No, milk is a colloid. We know milk is nothing but water and fat. Iron. Yes, iron is a pure substance, because iron is what? See, Ice is what? H2O. H2O is compound. Iron is what? Fe. Fe is metal. Metal is element. Right? So ice is yes, milk is no, iron is yes. Hydrochloric acid, HCl. So HCl is a compound, hydrogen and chlorine. Yes, it is a pure substance. Calcium oxide, CaO. It is again a compound. Compound is nothing but a pure substance. Yes, it is. Mercury, mercury in thermometer. Yes, it is a pure substance. It is an element. Brick. No. Brick has so many substances in it. It has soil. Soil itself is not a pure substance, right? So brick is not a pure substance. Wood. No. Wood is also not a pure substance. Wood also has so many things. Cellulose, nitrogen, so many things it has. So wood is not a pure substance. Air. Now air, if you know, air has oxygen, has nitrogen, has argon, so many other gas. So air is also not a pure substance. Okay. Identify the solution among the following mixtures. All these are mixtures. All these are mixtures. I have to find which one of these is solution. Right. So for solution, what we know is it will be stable. Correct. Particle size is very small. Particle size is very small, and no Tyndall effect. Okay, so let's see. Soil. Soil, if you see, it has so many things. It has so many minerals, right? It has dead bodies of the plants also. So it is not a solution at all. It has so many particles, so many big particles. It is a big, it is a, and in fact, solution has to be homogeneous, right? So this is a heterogeneous. So soil is not a solution. Seawater. Seawater has NaCl, correct? Seawater has water, plus seawater has some minerals, but it is a homogeneous mixture, right? And if you take seawater, you will see it will not show Tyndall effect as well. Since it is homogeneous, I can say yes, seawater is a solution. Air. Air also, if you see, air actually is a colloidal solution, right? Air is a colloidal. We have seen that, and that's why if some light comes from in a dark room from some window, you will see that Tyndall effect, right? So air is also a colloidal solution. So when we talk about solution here, I'm talking about both colloidal solution and a normal solution. Coal. Coal, if you see, coal has so many particles, right? Coal has carbon, so many impurities, and they are all heterogeneous. If you take some coal from here, some coal from here, it will have different composition. So coal is not a solution. Soda water, yes. Soda water, if you see, it has soda and water, and it is, and it has carbon dioxide also in this, and it is totally mixed properly. It is a homogeneous solution, so it is yes, a solution. So Tyndall effect is closed because we are talking about both colloidal and solution. If you talk only about solution, then you can remove this air. Which of the following will show Tyndall effect? Tyndall effect, you put a laser light and you see a dispersion of light, scattering of light. So if you see a scattering of light, then it is a Tyndall effect. Salt solution, we know it is pure solution, so it will not show Tyndall effect. Correct? Only colloids show Tyndall effect. Milk, yes, we know that milk is a colloid, so it will show Tyndall effect. Copper sulfate solution. Copper sulfate also is not colloids, actually. It is a normal solution, so it will also not show Tyndall effect. We have seen this. Starch solution is also actually not a colloid, so only milk will show the Tyndall effect. Classify the following into elements, compounds, and mixture. Sodium. Sodium is in the periodic table, so it is a element. Soil is a mixture because it has so many things. Sugar solution has sugar and water, so it is again a mixture, right? Silver is an element, it is in periodic table. Calcium carbonate is again an element, it is a compound. Actually, it's not element, it's compound. Tin is an element because it is in periodic table. Silicon is in periodic table, it is an element. Coal. So when you talk about coal is a mixture, we just saw, right? It has so many impurities and all. Air. When you talk about air has oxygen, nitrogen, carbon dioxide. It is a actually colloidal solution, so I can say it's a mixture. Soap has so many things. So many compounds mixed together. It's a mixture. Methane is CH4. CH4 is again compound because it has elements, right? It is compound. Carbon dioxide is again compound because it's CO2. Blood, if you see, is colloidal. We have told you this. Blood is colloidal. If you take some drop of blood in the water and mix in water, you will see the Tyndall effect. Blood is a colloidal solution. So with this, we can classify these elements into things into elements, compounds, and mixture. Okay. Next is which of the following are chemical change? See, growth of a plant, is this a chemical change? I don't think so. Plant is still the plant. There is no chemical reaction there, right? So it's all same. If it's growing, is a physical change. Rusting of iron, yes, because iron becomes Fe2O3. This is rust. You will study in higher classes. This is iron, pure iron. So from element you are making compound. This is sure short of chemical change. Mixing of iron filings and sand, no. If you mix iron filings and sand, there is no chemical reaction. Just a physical reaction, physical change. Cooking of food, yeah, I can see that the food gets cooked. There's some reaction happening in the cook because it happened at the high temperature. So cooking of food will be a chemical reaction. Digestion of food, yes, because we eat something, we eat carbohydrates, everything is broken into energy. So that is, yes, a chemical reaction. Freezing of water, no. Water, when you freeze, it is just a physical property change, right? This is still H2O, this is also H2O. There is no chemical change, just a physical change. Burning of candle, yes, because the wax is converted into chemical energy. So this is a chemical change. It's also a physical change as well, but this is a chemical change also. So this is a chemical change, yes. So these are the chemical change. The one in the correct is chemical change. There is rusting of iron, cooking of food, digestion of food, and burning of candle. They are the chemical changes. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.